That's what I like about teaching something 3 times. If I don't like the first one, delete, start over. All right. All right, so I need to make sure we know how to take square roots. And there's the way I teach the way square roots. And if this is how you learn, great. If not, I'd like you to consider taking square roots this particular way. So, for example, if I want to find out the square root of 8, the way that, like if you were taught taking square roots, where you basically do this little factor tree and start taking out pairs, that does work. I don't think that's super efficient. The way I break up, anytime I take square roots, the way I look at it is I think, well, I'm going to break it into 2 parts. I'm going to break it into something I know the square root of and what's left over. So in this case, that's going to be the square root of 4 times the square root of 2. I know what the square root of 4 is. Well, that's just 2, and then I have leftover square root of 2. Okay. Now, this works for, let's say I want to take the square root of 20. Again, I'm going to break it into what I know the square root of, break it into a perfect square and what's left over. And so this one gets to be, 4 and 5. I know what the square root of 4 is. I get 2 and then square root of 5. Okay. Just curious, I can do a quick survey. Is this how y'all were taught to do it, or were you taught to do it with the little factor tree? Okay, so the problem with the trees is those trees can get really long, right? Okay? What if I do something like the square root of 32? Then those trees get really long, don't they? Right? Now, there's 2 ways to deal with the square root of 32. I'm still going to approach it, think of a perfect square and what's left over, and you could think, well, 32 is 4 times 8, and you're absolutely right. I can break this up as 4 and an 8. I'll take the square root of each of those, so the square root of 4 is 2, and then I get the square root of 8. But then I have a problem. Well, not a huge problem, but the square root of 8 we can simplify because I've already made you do that, right? So you kind of ignore the 2 and you think, well, what's the square root of 8? Well, that's going to be 4 and 2. And so that gives me 2 square roots of 2. I still have my 2 from here. And so my final answer is 4 square roots of 2. At which point you're thinking, how on earth is this faster than me doing the factor tree? Well, this isn't, right? But let's say that you looked at that 32 and you said, well, wait a minute. That's 16 times 2, because 16 is a perfect square. And so if you looked at this and said that 32 is 16 times 2, and you said, oh, well, that's 16 times 2, and then the square root of 16 is 4 square roots of 2, that probably is faster than doing your factor tree. All right? So while I've sort of got you here as far as simplifying square roots, there are a handful of square roots that keep showing up, and if you just sort of recognize, when I say handful, I think there's 4. I want to talk about these 4 square roots, and they just keep showing up, and your life's a lot easier if you just know them. So the 4 that keep showing up that your life's a lot easier are the square root of 32, the square root of 48, the square root of 72, and the square root of 80. Okay? So, not asking you to write down a whole lot, I'm just saying this is going to make your life easier if you know these little square roots. So, 32, we've already talked about this. This is the same thing as 16 times 2. So I end up with 4 square roots of 2. If you look at square root of 48, that's the same thing as 16 times 3. And so I end up with 4 square roots of 3. If you think of 72, well, that's going to be the same thing as 36 times 2. And so we end up with 6 square roots of 2. And 80, we're going to think of that as 16 times 5. And so that gives me 4 square roots of 5. So, in simplifying square roots, your life's just a lot easier if you can remember these. I mean, there's some of the other ones like square root of 18 that come out pretty, you don't have to work too hard on. These are the ones that tend to, you got to recognize you can do them, like 32, if you do it the inefficient way, it just takes a while. If you realize, oh, that's 16 times 2, then it's a lot faster. Well, for this method to work, that means you need to know your perfect squares, right? Like most people know when I say know your perfect squares, I mean, like know them at least 20. Like you need to know that 16 squared 256, 17 squared is 289, right? I'm not going to write the perfect squares from 1 through 12 because you know those, but you need to know that 13 squared is 169, 196, 225, 256, 289, 324, 361, and 400, right? So that's 13 squared, 14 squared, 15 squared, 16, 17, 18, 19, and 20 squared. It's also handy to know that 25 squared is 625. It's nice to know what 21 through 24 are, but in the big picture, these are the things that, if you ever see this is a perfect square, I know I can take the square root of it. Your life's just going to be a lot easier if you know those. All right. Oh, another trick as far as simplifying square roots. What happens if I give you the square root of a pretty large number? Like if I said, what's the square root of 363, right? And this method that I told you kind of depends, you got to recognize what's a perfect square that goes into this. It's like, I don't know, right? It's like everything I've shown you, granted I've gone through, you've gotten the very condensed version of it, is think of a perfect square, and so you think, oh, there's a perfect square, and then there's the other number, right? So there's something I know to take the square root of, and then this thing that's left over. Well, okay, here's a secret. Most problems math teachers give you when you're simplifying square roots are going to have a square root of 2 left over, or a square root of 3 left over, or a square root of 5. You might have a square root of 7 or a square root of 11, but for the most part, it's going to be 2, 3, or 5. So instead of, when the numbers are big, instead of thinking of the perfect square, like we're going to break this into, this is something I know to take the square root of, and this is what's left over. So instead of trying to figure out what the perfect square is, sometimes it's easier to figure out the number that's left over. So you're not looking for a perfect square, you're just saying, okay, does 2, 3, or 5 go into this? So if you had to pick a number that goes into this, would you guess 2, 3, or 5? 3, right? Pretty, right? Well, look what happens if you say, well, okay, I don't know what the perfect square is, but I know 3 goes into it. So if 3 goes into it, what's this number? 121, right? Do I happen to know the square root of 121? Yeah. So this gives me 11 square roots of 3. Little trick, right? And it's kind of knowing that when teachers give you problems like this, it's either going to end in a square root of 2, square root of 3, or square root of 5. And knowing that kind of helps out. All right, so brief review of square roots. Now that we talked about square roots, I need to talk about how do we take the square root of something like the square root of negative 9? So, how do you do that? Well, I don't know, right? And mathematicians didn't know for a long time either. If you ever look at the history of sort of the development of mathematics, it wasn't until like 1700s that they even acknowledged negative numbers existed. Basically, if there was a negative number, they said, nah, we're not going to worry about it. We don't deal with those. Those are negative. We don't deal with those. Apparently, nobody ever owed money. But, if you negative numbers, they just didn't care about it. So, I know, it's a pain. So how do you take the square root of negative 9? Well, let's think about square roots for just a second. If I were just taking like the square root of a positive 9, and the way I was taught in school was think of a number times itself that gives you 9. And you think, well, 3, right? Because 3 times 3 gives you 9, so we know that works. Well, when you think of a number times itself that gives you negative 9, it doesn't quite work, does it? Okay. Well, 3 doesn't work, because 3 times 3 gives you positive 9, and negative 3 doesn't work, because negative 3 times negative 3 also gives you a positive 9, right? So we have a real problem. Like, we can't deal with square root of negative 9. And actually, the issue isn't the negative 9 part, right? Because every square root you can break up. just like I broke all these up. So I'm actually going to break the square root of 9 as the square root of -1 times the square root of 9. Right? Because, see how we can break all those up?
Yeah.
So if I can break those up, I can handle the square root of 9 just fine. That's 3. But I can't handle the square root of -1. Right? So what is the square root of -1? Now, so the first guy that actually thought about dealing with the square root of -1 was a guy named Frederick Karl Gauss. We're in the early 1800s, and he actually came up with some very interesting things with dealing with square root of -1. Now, and he kept writing square root of -1, and he did a whole lot of math, and there's a guy named Riemann that did some amazing stuff with square root of -1. And kind of in another 50 years passed, and there was a guy named Euler that got tired of writing square root of -1, and so instead of writing square root of -1, he decided that since it's not, it doesn't exist, because that square root of negative really doesn't exist, he decided to call it an I. Right? So, when the guy named Euler came up with this notation, he had this idea that instead of writing square root of -1, we're just going to write I. Right? For imaginary. Like, remember, mathematicians really don't like dealing with negative numbers anyway, and really didn't like dealing with square roots of negatives. So anytime you see the square root of a negative, you think, okay, well, I'm just going to break it apart, and I'll say, oh, well, anything that's square root of -1, that's just, we're going to call it I. All right, so what does that mean for you? Well, at a very basic level, so back to this problem, if I wanted to know the square root of -9, I would write that as 3i. Right? Because the square root of 9 is 3, the square root of -1 is I. How would I write the square root of -12, right? Like, how do you write that? Well, what you do is anytime you see the square root of a negative, you know you're going to have I in your answer. All right? And since we know we're going to have I in the answer, like, I'm going to break this apart, and I'll say, well, that's going to be the square root of -1 times the square root of 12. Well, I know that's going to give me an I, and then I got to think, well, how do I get the 12? Well, let's see. That 12 is really 4 times 3. Square root of 4 I know is 2. I don't know the square root of 3, so that gives me I times 2 square root of 3. All right. Now,
Does the I have to come first?
no, actually I want to talk about where you put the I. So where does the I go, right? Okay. Technically the I can go anywhere, right? You're multiplying, it doesn't matter, right? If this was a problem in your textbook, the way the textbook would actually write it, they would write this as 2i times the square root of 3. They usually stick it here. It's not wrong this way, but this is how they would write it. Now, let's talk about how do you handle something like, what about the square root of -5? Well, when I break this apart, I think we all know there's no square root of 5. There's no way we can break this up. So we know we're going to have a square root of 5. And we also know because we have the square root of a negative, we're going to have an I involved, right? So where do you put the I? And honestly, it doesn't matter, right? You can put the I in front. You can put the I here, right? The sort of the standard way is you put the I in front, and here's why. Let's say that you put the I here, right? And there's nothing wrong with that. Mathematically, it's fine. But you're not real careful how you draw your square root symbol. And if you're not real careful how you draw your square root symbol, your square root symbol might be a little longer, right? And now, this is now the square root of I, as opposed to the square root of 5 times I. Do you see how that's different? So one way to avoid that altogether is you stick the I in front. That way you know the I is not inside the square root. If you stick the I off to this side, there's the potential that you may write it such that the I is still inside the square root, which is bad. So, all right, so when you take the square root of a negative, actually, I'm just curious, have y'all talked about the square root of a negative number before?
Just kind of ignore it.
Okay, good, just like all the mathematicians before, right? It's a square root of negative, we don't like it, we'll just ignore it. I'm not kidding. It wasn't really until like the 15 or 1600s that people just started acknowledging that negative numbers existed, which seems kind of silly, but that's it. All right. But when you take the square root of a negative, you get an I. Yay. So what does that mean? Well, one thing. So if I start now, so here's something you probably want to write down. So I have this idea that I is equal to the square root of negative 1, which means if I square both sides, I'm going to get I squared is equal to negative 1. Is everybody okay with this part? If I is equal to the square root of negative 1, if I square both sides, I get I squared equals negative 1. And this is kind of this is kind of the rule, they say. And they really, really do this a lot. Yeah. They're real big. I squared equals negative 1. Okay? And the rest of today's lesson is going to really work on this idea that I squared equals negative 1. Right? There's two ways that we're going to use this. One is figuring out different powers of I, and the other is kind of treating I like a variable. But we're going to get to it. First, we're going to talk about I to a bunch of powers. All right, so we start. If I want I to a bunch of powers, I guess I better start figuring out I to a bunch of powers. I've got I squared as negative 1. I cubed, well, so I cubed, anytime you see I to a bigger power, you break it apart into stuff that you know and then the leftover. So for example, I cubed is the exact same thing as I squared times I, because that altogether is I cubed. And what's I squared? Negative 1. So I get negative 1 times I, which is going to give me negative I. All right? I think about I to the 4th. Again, I'm going to break it into what I know, and I like I squared, right? Because I squared is negative 1. That's pretty simple. So when I break I to the 4th, I'm going to break I to the 4th as I squared times I squared. So that's going to give me negative 1 times a negative 1, which is going to just give me 1. Huh. But I want to summarize this, right? So to summarize this, let's see. I to the 1st is just I. I can't do a whole lot with that. I squared, we talked about that's negative 1. I cubed, well, that's going to give us negative I. And I to the 4th, it gives me 1. I did say that we're going to find I to a bunch of different powers. So let's talk about I to the 5th. I need some room, so I'm going to write over here. I want to talk about I to the 5th. Well, you know, I to the 4th is pretty nice, right? Because anytime you see I to the 4th, that's just 1. So I could think of I to the 5th as the same thing as I to the 4th. Actually, I'll do it over here. I to the 4th times I. Because altogether, that's I to the 5th. Well, what's I to the 4th? 1. So that's a big fat 1 times I, which just gives me I, doesn't it? All right. Let's think about I to the 6th. Well, I really like I to the 4th. Since I really like I to the 4th, I can say this is I to the 4th times I squared. And so we end up with, that's a 1, and that's a negative 1, right? So that's a 1, and that's a negative 1, and so my answer is going to be negative 1. Well, let's talk about I to the 7th. Any guesses as to what I to the 7th is going to be? Negative I. And we got I to the 8th. 1. Huh, that's interesting. So 1, I, negative 1, negative I, 1, and then I, negative 1, negative I, 1. Huh. Guess what I to the ninth is?
Well, I.
I.
-1.
-1.
-I.
Negative I. And then 1, right?
1.
We get this little pattern, don't we? This little cycle of 4. It does the same thing, right? Over and over. All right? So, how do you answer something like I to the 33rd power, right?
Divided by 4.
Okay. Okay. So let's talk about what is, what's helpful. I don't know if you picked up as I was presenting this, I said I really like I to the 4th because I to the 4th is 1. Well, I kind of lied. I didn't lie. I do like I to the 4th. It makes life easy. But I like I raised to a power of 4, a multiple of 4. See, I to the 4th is 1, I to the 8th is 1, I to the 12th is 1, I to the 16th is 1, I to the 20th is 1, right? If you have I and it's a multiple of 4, like think of your 4, like your multiplication tables for 4, you get 1. And so when you look at this, you think I to the 32nd, I to the 33, I don't like 33 so much. What number do I like?
32.
32. And so I get I to the 32, and what's left over is the I, and so that's a big fat 1. And so I get 1 times I, which gives me I. Does that kind of make sense? So anytime you have I raised to any power, it's going to be one of these, right? If it's raised to an even power, it's either positive or negative 1. If it's raised to an odd power, it's either positive or negative I. And how do you figure it out? Well, it all hinges around pretty much how well you know your multiples of 4. So, that's fine, I give you this. Well, what if I said, what about I to the 106th power? Right. So now you gotta think, okay, multiples of 4, right? You go, okay, how do we do this? Multiples of 4, I've got, it's, okay.
-1.
Yeah. Okay. All right, I'll call on you. Arjun, I'll call on you when I need you to say something. Okay. Okay. So, when you look at it, you want to think of what's your thing of, I need to think of what's a multiple of 4. And there's a trick, right? I don't know if you know your divisibility rules, right? But if I ask, does 4 go into 12? You go, of course it goes into 12. If I say, does 4 go into 24? Of course 4 goes into 24, right? But if I say, does 4 go into 224? You go, maybe, right? It's a bigger number. You've got a 50-50 shot for the most part. And here's the rule for divisibility by 4. Anytime you get a 3-digit, anytime you have a really big number, if 4 goes into the last 2 digits, it goes into the whole thing. So, if I say, does 4 go, what's the nicest power of 4, multiple of 4? 104 is. And so this is going to be I to the 104, and what's left over is I squared. And then this is a multiple of 4, so we get a nice answer. We get our 1, and then we get I squared is -1 as our answer is -1. All right. So, when you have, all right, so, and all of this really hinged, all of this stuff really hinged on just that one fact that I squared is -1. I mean, this whole chart was developed on this fact that I squared is -1. All right, next up, I have an algebra equation. So let's say I give you 3 minus 2x times 4 plus 5x. I want everyone to write this down and multiply it out. And when you've got it multiplied out, do the electronic raise your hand. put the x's in front, but I'm just being kind of weird right now. And so we multiply it, and this is going to give me 12. I get minus 10, minus 8 plus 15, gives me plus 7x, and this is going to give me a minus 10x squared. Dang it. I should follow my script. Pause. I'm going to back up. I should have just let pause and just start. We're going to come back to this. But I forgot there's 5 minutes of something I needed to talk about before this part. We don't erase it. We're still going to use it. Not just, okay. All right. So I need to talk about different types of numbers. Up until this point, we talk about real numbers. And in real numbers, you got like rational, rational, irrational. You got whole numbers. You got counting numbers and natural numbers, like all that stuff. Usually in a regular Algebra 2 class, you spend a little bit of time talking about those, and to be honest, it's not super important. But these are real, right? And everything was dealing real. Today, I've introduced this thing called an imaginary number, right? It's not real. It's imaginary, okay? I know math people are, I'm not making up this vocabulary. You've got real, and then you have imaginary. But imaginary numbers are they don't just call them imaginary numbers. They call them complex. And here's an example of a complex number. The example of a complex number is something like 2 plus 3i. It's just, all right? Now, as far as the reason it's called a complex number is it's complicated. See, you have a real part and you have an imaginary part. And it's going to be really tough to figure this out. See, the real part doesn't have an I. And the imaginary part has an I. Okay? I'm sorry, being a little sarcastic on this. But the reason it's called a complex number is it's a number that has two different parts. It's got a real part and it's got an imaginary part. And we are dealing, in fact, this section is dealing with complex numbers, meaning we're dealing with numbers that look like this. All right? So I'm going to put some examples down. If I give you 3 minus 4i, that's a complex number. You know why it's a complex number? Because it's got a real part and it's got an imaginary part. Okay. If I give you, let's say I give you 3i, is that a complex number?
No.
Actually, it is. It's kind of a trick question. See, the reason it's a complex number is it still has a real part and imaginary part. The real part happens to be 0. 0 is a number, isn't it?
Yeah.
It's a real number, okay? So believe it or not, this is a complex number. And on that same vein, if I give you 5, this is a complex number. Why is it a complex number? Well, because I can put 5 plus 0i.
So is everything theory than a complex number?
Yeah, so believe it or not, everything is a complex number. And what we're going to find out once we start our next chapter is that when you deal with everything other than complex numbers, things get way more interesting because you're not just looking at certain things. Okay. Now, as far as giving you, so just if you see a 3i, that's still classified as a complex number. If you see a 5, you can still classify that as a complex number. Just the complex part happens to be 0.
What's the definition of complex number again?
It has both a real and imaginary part.
Would pi be a complex number or like imaginary number?
So what? What and what?
Pi is in like 3.14.
So pi is, so I could, if I wanted to write its full complex version, I could call it pi plus 0i. And the real, so one thing, I can note it, I wrote the chart, I said this is real and complex. Actually, it's complex. That's the overarching thing, and then you have real. Then you have a subpart of complex is real. A subpart of in real, you can break real into rational and irrational. And pi falls into that irrational part. And that's a discussion that was actually from chapter 1 in your book that somehow the state of Georgia didn't think it was important to talk about, so I haven't. Okay. And I've got some other things I need to do before today. So, so to talk about a complex number, okay, it's got an I with it. And typically when they say want your answer in terms of a complex number, you'll see this thing A plus BI, where A and B are like constants. So there's your A plus BI. All right, so I have 13 minutes. I want to see what I can do. There's 3 things I need to teach in 13 minutes. And one of them I don't really have to teach because you'll get it right. Here's the first thing. If I give you 3 plus 2i plus 5 minus 3i, this is what I like about being a teacher for this stuff, is I don't have to teach. I can just say, I can put this on the board and I'll say, treat the I like an X and give me your answer. Right? You don't need a teacher for this. I can just look at this and say, no problem. Say 3 plus 5 is 8. 2i minus 3i is a negative I, and I'm done. Here's what you've just done. You have added 2 complex numbers together. What'd you do? The same thing you did in Algebra 1. You just treated the I like an X. Right? Isn't that the same thing you did in Algebra 1? You just treated the I like an X. Right? And that's pretty much what we're going to do. Anytime you see an I, just treat it like an X. So if I ask you to add, you add them. If I say put a minus sign, you subtract them, right? All right, now I made that up. What was the number, the two binomials that I had you multiply together? 3 minus 2x, and then what?
And then 4 plus 5x.
4 plus 5x, all right. So I asked you to multiply those together, so you already have that answer. You've got 12, you got plus 7x minus 10x squared. Everybody get that? So you just multiply, right? You just treat an x, right? It was an x. So now I'd like you to do this same problem, but now instead of an x, I want you to think of this as 3 minus 2i times 4 plus 5i. And you know what you do? The exact same thing you did when it was an x. So if you do the exact same thing you did with an x, you're going to write this down as 12 plus 7i minus 10i squared, right? We did the same thing, right? I mean, that's what I told you to do, right? I said when you see an I, you treat it just like an X. And so I saw an I and I treated it just like an X, right? And so I got the same answer as I got up here, except now I have I's instead of X's. And here's the difference. Remember that little rule we had? That I squared is equal to negative 1? Well, do we have an I squared? That's a negative 1, right? So if you have an I squared, that means you've got to write that as a negative 1. So that's going to give us 12 plus 7i minus 10. And now when I look at this, now when I clean it up, so that's going to make that a plus 10. So I get 12 plus 10. It's going to give me 22 plus 7i. Notice when I multiply 2 complex numbers together, I got a complex number. All right, your turn. So I give you 2 plus 3i times negative 3 plus, that's a 3, plus 5i, and then 6 minus 5i, that's 4 minus 3i, and then 2 plus 3i, that's 2 minus 3i. I want everyone to multiply these three together. I want everybody to multiply these three problems together. But I need to make sure there's actually two more ideas I need to talk about. I don't think I'm going to get to both of them, but I at least get to one of them. All right, so the first one, let's see, we multiply it together. Let's see, that's going to give me negative 6 minus 9 plus 10 gives me a plus I, and then I get plus 15I squared. All right. Just treated that I like an x. But if you have an I squared, we have to write that down as negative 1. So remember that's a negative 1. And so negative 15 minus 6 gives me negative 21 plus I. Okay? Same thing over here. We're going to get 24. That's minus 20 minus 18 gives me minus 38i. Then I get plus 15i squared. But I have an I squared. And since I have an I squared, I'm going to have to change that to a negative 1. And so that's going to be 24 minus 15. So I end up with 9 minus 38i. All right. And the last one. Oh, kind of looks like a difference of squares. See, whenever you look at two binomials where they're almost the same except one's a plus and one's a minus, you get a difference of squares, meaning that middle term cancels. And so if that middle term cancels, let's see, I'm going to get 4, and then I end up with a minus 9i squared. Of course, that I squared is a negative 1. So I can go ahead and erase that and make that a negative 1. And so that gives me 4 plus 9, which gives me 13. So, a couple of things I want to talk about. Notice, I think I already mentioned this part, notice when you multiply two complex numbers together, you get a complex number, right? Same thing over here, I multiply two complex numbers together, I get a complex number. This one's kind of interesting. It's a complex, technically it's still a complex number, but notice it only has a real part, right? And the reason it only has a real part is the middle term got canceled, right? This has a special name. These are called conjugates. Anytime you're where you're creating a difference of squares, 2 minus 3i is the conjugate of 2 plus 3i. And actually creating conjugates is a big deal. Right? And that's probably where I'm going to have to pick up tomorrow. Or I'll talk about it a little bit and then I'll have to sort of clean it up tomorrow. Where I'm going with all this. So, I don't know if you noticed, but I multiplied two complex numbers together. Everybody see? Complex number, complex number. So, if you think about what we've done, I've added and subtracted complex numbers, I've multiplied, guess what's next? You divide, right? Okay? So, how do you divide complex numbers? Like, how do you multiply complex numbers? Well, we kind of multiplied, right? We have to sort of treat it like our regular algebra stuff where we multiply. What does a division problem look like? Well, here's what a division problem looks like. Our division problem looks like this. Let's say I give you 3 over 2 plus 3i. And this is going to be it. I may be pushing it doing this one part. Your job, and this is what we'll pick up tomorrow, is you got to get rid of the I in the bottom. Right? That's your job, right? Technically, as I as a square root, you have to rationalize your denominator. And the trick is you have to multiply by the conjugate. Right? Whenever you have a fraction, the only thing you're allowed to do is multiply top and bottom by the same thing. And so when you have a fraction, what you have to do to get rid of this I in the bottom is we're going to multiply top and bottom by 2 plus 3i. And I'm going to stop here.